Let's start with normal distribution also. We have seen this before. I'm just going to do it here because it's important. We will probably need it later on. So what is a normal distribution? The density has a bell-shaped curve. We know that. So if X is normal, mu comma sigma squared, mu is the mean, sigma squared is the variance. Okay, so if X is normal mu sigma squared, then f of X, the density, is 1 over sigma square root of 2 pi e raised negative 1 over X minus mu over sigma squared.
And that's a generalization of the bell curve, like e to the minus x squared.
Yes, this is not a specific case. The special case is the one that I'm going to write next. So that is for any random variable. You might have seen this transformation in 2023 when they said we're going to convert an x value to a z-score by subtracting the mean and dividing the standard deviation. It's exactly what's happening here. So if I did that, then Z would have a normal 0, 1 distribution. Normal 0, 1 is what we call a standard normal distribution. Good. Your book uses phi. They do it in a funky way. I write phi this way. Phi of Z is the density of a standard normal. Can you tell me what that density is by looking at it? 1? No. What is the density phi of Z? I've given you the density for a normal mu comma sigma squared. I would like to know the density of a standard normal. It's easy. Just have to plug in values. Do you follow my question? I've given you the density for a normal mu comma sigma squared distribution. I would like to know for a normal 0, 1. Okay.
You plug in 0 where mu is, you plug in 1 where sigma is.
Okay, so mu is 0, sigma squared is 1, which would mean sigma is 1. So 1 over 1 times square root of pi, square root of pi, e raised negative 1/2. That would simply become that square. Good. So both of them would have a support from negative infinity up to positive infinity.
And in this case, z equals x, right?
What do you mean z equals x?
Well, if mu is 0 and sigma is 1, then you can plug in and see it's negative 1/2 times x minus 0 over 1 squared, so that's negative 1/2.
Right, but I want to distinguish the standard normal from a normal, because standard normal is a case that is related to the z-scores that we always use. When we say normal, it could be any normal distribution with any mean, any standard deviation. We want to be specific, that's why we use this. The cumulative distribution function denoted by uppercase V of Z just going to leave it as is. We know we can integrate this to get the CDF of Z. I'll just leave it as is. So probability Z less than or equal to lowercase z. I'm just shrinking the uppercase Z to get a lowercase z, yes.
So is that the same fee as you wrote down there?
This is lowercase and uppercase. You know, people write fee that way, but I write it this way. So why do we have this? So if X is normal with mean mu and variance sigma squared, then the PDF, excuse me, the CDF of X is probability of X less than or equal to X. So if we want to find the probability of X less than or equal to X, it is the same as the probability of Z in the sense probability Z less than or equal to Z. In other words, you've got to transform the random variable from X to Z, lowercase x to Z, then you could use the standard normal to find the probability. Does that make sense? So if I subtract by mu, right? I will have X minus mu and divide by the standard deviation. X is a random variable, so uppercase X, random variable minus mean over sigma would result in uppercase Z. A number from that normal distribution minus mean over sigma would give you some value Z. So if I want to find the probability, CDF, cumulative probability of some random variable with mean mu and standard deviation sigma or variance sigma squared, I can transform it in this manner so that I can use the standard normal distribution. So the key step is to transform. Good. I mean, these are things that you probably know already, but see about my bell curves. Standard normal, right? So if I pick some Z value on this side, some Z value on that side, then phi of minus z, in other words, the cumulative probability less than or equal to minus z would be equal to 1 minus the cumulative probability of z. What we're trying to say is the area over here of the cumulative probability over here would equal the cumulative probability over there. Good.
So down the middle, that's 0 and sigma squared equals 1.
Yes, that's correct. Sorry about that. Uses the density phi of minus z is equal to phi of plus z, right? So negative, in other words, the negative of a normal variable is the same as a standard normal variable, because we have the density to be 1 over square root of 2 pi e raised minus z squared over 2. So if you change z by negative z, you will still get the same function, which would make the density function even. And because of this even symmetry, that holds true. So those two are related.